right? So it's just easier to prove that H is a normal subset by showing that all members of X inverse HX belong to H. That's easier than proving equality between two sets. Well, generally speaking. Okay. So in the problem-solving session, we will probably solve a couple of problems of that type. Prove that this subgroup is normal. It's a normal subgroup, right? Okay. So next little result here. A few things on the side. If your group is abelian, then all subgroups of that group, that abelian group, all subgroups are normal, right? In the special case that it's abelian. And to prove that, well, just a lines proof. So, for any x of your group and any h of your subgroup, then here's your form. Now, we're trying to show that this H is a subgroup, right? Now, from what I just said before, we don't have to do this. We just do this, right? Just show that it's the left-hand side here is a subset of H. That's all we need to do, all right? Well, take any H from your subgroup, big H. So you'll have this form. Now, H and X commute, right? It's an abelian group. Any pair of elements of your group commute. A, B's, BA, right? So we can swap these two around. So HX becomes XH. And then you've got X inverse X. Well, that's just E. So EH is just a little h. Well, by definition, little h belongs to the subgroup, right? So that means this, no matter what X is, it's just equal to H. And since H belongs to the subgroup, this will belong to the subgroup, right? And that's true for any element X. So you've got that. That's true, right? So therefore, for an abelian group, all subgroups are normal. Okay. So that means you can find. Well, I'm jumping ahead a little bit. That means you can find quotient groups for abelian groups easily, because all subgroups are normal. Okay. All right. So now we're sort of getting closer to the heart of the matter. This idea of a quotient group. So to get closure, when we took cosets and we used subset. Yeah, we used what I called subset multiplication to take two cosets and multiply them together to get a new, or to get usually another coset. Right? So if that subset multiplication, if that's your binary operation on two cosets, and if your subgroup H is normal, you have those two conditions, right? Then is the set of your cosets, the cosets of H, that set of cosets, is that then a group? And the answer is yes, right? So for any group, it consists of a set and a binary operation on that set. That's with the four conditions, of course. That's a group, right? So the set now for we're heading towards definition of a quotient group. So that the set are the cosets of your H, of your subgroup, right? That's your set. So it's a set of cosets. So it's a set of sets in a sense, right? So your set is of the cosets of H, right? The binary operation is what I called subset multiplication. We did an example of it in the previous session. and we'll do some problem solving as well. Okay. Now let's try to prove that this set of cosets, the cosets of H, with this binary operation of subset multiplication, so, that's actually a group, right? So we need to prove, the usual, you need to prove the four properties hold. Now we've already done closure, because that was the whole point of deriving this idea of subset multiplication and the idea of a normal subgroup and so forth, right? So we've already done the whole discussion on closure. That's where the concept of normal came from in the first place, right? So we've set things up and created this idea of a normal subgroup to get closure, right? That was the whole point. Okay, so closure's done, right? So to get closure, we derived this. In fact, we did it both ways. So your binary operation on two cosets of H is closed if and only if this. Remember that relation previous session? Okay? So we have, remember that's like one result. But from theorem 58, the one before this, and here I've written it down again to remind you, theorem 58 says if this is true, right? This if and only if H is normal, right? H is a normal subgroup. All right. Well, we can now combine these two. Right? Look, we have closure if this, and 58 says if you have this, H is normal. Well, that's of the form if A then B, and if B then C, and you're given A, well, therefore C, right? So we can, from these two together, we can conclude closed if and only if H is normal, because this and this are the same. So this is true if that's true, and that's true if that's true. This is true if that's true. If this is true, that's true. And if this is true, that's true. Right? Therefore, if this is true, that's true. Right? So if closed, well, closed if and only if H is a normal subset. All right. Okay. So if you have, in other words, if you have a normal subgroup, your binary operation on two cosets of H, big H, is closed. Okay? And the other way around, if that binary operation is closed, then you know H is normal. Right? Both ways. Okay. Now we can get to the nitty-gritty. I mean, the heart of the chapter, right? Which is one of the highlights of the course. So trumpet roll, ba-da-da, theorem 60. Okay. H is a normal subgroup of G. Right? The set of cosets of H, where the binary operation, I've got a little circle here, binary operation, is subset multiplication. Right? So you're given this set of cosets of H. The binary operator is subset multiplication. In other words, your subset here is the cosets. So you multiplying two cosets, right? That duo, the set of cosets, with this binary operation, forms a group. Okay. Now we've done closure, so let's do the other three properties and show that that you actually have a group, right? With this set, the set of cosets, and the binary operator being the subset multiplication. All right. So we've done closure. How about associativity? So if you have three cosets, let's say AH, BH, CH, are those three cosets when you multiply them together, using subset multiplication? Do you get? Is it associative? Is that multiplication of three cosets? Is it associative? So we're trying to show that now here's a product of three cosets, right? And the binary operation here and here is subset multiplication, right? So we're trying to show that this equals that. In other words, multiplication of three cosets is associative. So if you multiply these two first and then do that later, will you get the same result as if you do these two first and then multiply by the third one? Well, let's show that they are the same. So we can rewrite this BHCH as BCH. That's just an example, that's just here, right? Using theorem 58. Because why? Now this is an if and only if 58, right? So, but we're given in theorem 60, we're given that H is a normal subgroup. So if H is normal, we go from right to left, and we have this. So we can use that, right? We can use it here. So BHCH is just BCH, right? And use the same thing again. So now we get A brackets BCH there, right? So that's the result of this one. Now, how about the other way? When you do this,